Therefore, your f is homomorphic. All right, so you know it's homomorphic. Now, how about surjective? So surjective, that means every element in your codomain is mapped to, right? There are no loners. So, well, let z be x plus I 0, right? So we're just taking the real part of a random complex number, so x plus I 0. And if you take the mod of that z, you'll get mod x, and that could be anything, right? Now remember, z is non-zero, right? That's what the star means. Z is non-zero. It can be anything else, but not zero. So therefore, this x here cannot be 0. Follow that logic? So if x is non-zero, mod of x has to belong to R plus. This cannot be 0, so anything else, modded, absolute value of, gives you R plus, right? And that x can be anything. So this value here is all the positive reals except 0. In other words, R plus. Okay. So in other words, every value of R plus here is mapped to by this z. I mean, you can find a z of this form, x plus I 0, that maps to any value in R plus. So it's surjective. This f is surjective. All right. Okay. So as usual, find the image, find the kernel, and then apply this. So what's the image? The image of f. What does that mean again? The image of f? It's the set of all possible f's values, all different f values. Well, f will map z into mod z, right? And this mod z is just, it belongs to real plus, R plus. So any value in R plus can get mapped to, right? And your different values. So your image is just R plus. So can you follow that? What values can f of z take? Well, anything in R plus. So all of those possible values that get mapped to, all those different values of f of something, is just R plus, right? How about the kernel? The kernel. All right. So which values of z, which z's map to 1? It's kernel. So the kernel is the subset of your domain, your starting group, that map to the unit of the codomain, of the target group. So in this case, f of z has to be equal to 1. So the z's have to have a special property. So it's a set of all these z's that belong to non-zero complex numbers, but the mod of z has to be 1, right? For this z to belong to the kernel. Okay? So mod of z is 1. That's a condition in your set here. So call that set T, right? So in other words, this complex number z, its absolute value is 1, and therefore this complex number z lies on the unit circle, right, in your Argand, A-R-G-A-N-D, Argand diagram. You know, the diagram of the complex plane, x and y, where z equals x plus I, y, right, the Argand diagram. So this T is the unit circle in that Argand diagram, right? So z lies on the unit circle. Okay, so we have the kernel, we have the image, we know that this mapping function f is surjective, we know it's homomorphic, and therefore, you know, with all the theory we did, therefore the first isomorphism theorem holds, and therefore we can write the parent group slash the kernel, which is T, okay, is isomorphic to the image of f, which is so the sets R plus, right, and the binary operation, you know, to make it a group, because this is a group, this is a quotient group, right, and it's got to be isomorphic to a group, not just a set. So to make this a group, the binary operation here is just multiplying these real numbers. Well, yeah, I mean that's what we've assumed here. We're mapping this group into that group. Okay, so that's the end of the problem-solving part. Now, this is the end of the course, right? This is the last problem-solving session of the last lecture of this course. So now would be an appropriate moment to talk a bit about the future courses, which I'll split two ways. Future courses in this topic, the topic of finite group theory. So I will talk a little about that. I'll come back to this in a moment, and I will also talk about the next two courses that I'll be lecturing in. The next one will be on quantum mechanics. It'll be a physics course. Now, quantum mechanics is absolutely basic to physics, especially to graduate level theoretical physics, mathematical physics. So given its importance of the topic, quantum mechanics, I thought it would be very important to give people studying graduate level quantum mechanics a really thorough basis at undergrad level, in fact senior level, in quantum mechanics. So the next lecture set, the next course that I'll be teaching is quantum mechanics, and here's the text I'll be using. It's fairly thin. It's only about 160 pages, more or less, so hopefully I can get through it reasonably fast. But it's good. I was quite impressed by it. Nice compromise between its length, its level. It's definitely senior level, as the author, well, there are two authors. So here's the book. So it's just simply called Quantum Mechanics. It's the second edition, which is a good sign. And there are two authors, Davies and Betts. So here's the text. Okay, and it's available on eMule, so you can get it for free if you want. Although I'm starting to have question marks about that whole philosophy of using eMule for poor third worlders, and I'll be talking about that in a few minutes. Okay, so that's the physics course. That'll be the second course that I will be lecturing on, starting in a matter of day or so. And the third course, after I finish the physics course in a month or two, I'm a bit concerned about the rate I'm going at. So the third course will be on computer theory, because remember, or this whole lecture series, all hundreds of them in the next coming decades, are of type MPC, right? Math as in pure math, physics as in mathematical physics, and C as in computer theory, right? So the third one, just so that you can get a feel for you know, what I'm like at teaching computer theory. Maybe I should add that in my previous life I was a full professor in computer science, right? But I got bored with that subject, so now I'm arcing, I'm free, I do what I like, and what I like is mathematical physics, pure math and physics. So I know computer science. Anyway, here's the text of the first computer theory topic, and the subject will be on the theory of computation. You know, Turing machines, computability, uncomputability, stuff like that. Now I've got a Chinese version here because it was cheaper, but if you're buying the English language version, it would probably be this. This would be the cover of the book, and the author is Sipser, S-I-P-S-E-R, Sipser. Okay, and it's you can see from, it's pretty well double the thickness of the previous book on quantum mechanics, Davies. Now, this is like 400 pages, so that will take me quite a bit longer. But theory of computing, very important, because remember, one of my goals is to teach a generation of students, interested people who want to become experts in a new field. In fact, it doesn't really exist yet. It's still fairly new, but it's coming, and it will be revolutionary when it comes. If you have not seen my introductory videos, like intro to deGarisMPC, please go and look. One of my goals is to try to educate a generation of students in MPC, TQC, topological quantum computing.